Chat box participants. All right. Perfect. Welcome to the special lecture for CS 431 and 631. The reason we have these special lectures this week is that I'm going to show a tutorial during lecture, and we wanted to make sure that we use the correct or appropriate programming language for it, because the two different sections, they use different languages. So that's why we have a separate lecture for you guys today. So to start, we talked about this architecture for Spark, where we have a driver program and a bunch of worker nodes, right? And today we're going to learn more about them, and we see a nice tutorial and see how it works actually and how we can program in a Spark. Can you see my screen? Everything's fine? All right. So let's remind what RDD is. So if you remember, RDD is the data structure that we use to keep our data. It is different from regular variables that we use in different programming languages because it is actually a distributed data structure, which means that the content of this RDD is physically on multiple servers, okay? And if you remember, it's in the RAM. It's not on the disk, but it's actually in the RAM, and that's why we need multiple machines to keep track of the data. This is the logical view of an RDD, and this is how you should think about it when you program. An RDD is divided into chunks. Okay, because there's a lot of data, we need multiple machines, and so we have to divide it, right? Each chunk, the correct terminology is a partition. Okay, so this particular RDD has 6 partitions. All right. In practice, typically, or it's better to say, the default partition size in a Spark is 128 megabytes. Okay. So we divide the data into these smaller chunks and we assign them to different machines. But that would be the physical view. Okay, so let me explain the physical view of this now. So we have a driver program, right? And we have a bunch of worker nodes. And as we explained, all of these calculations and operations happen on these worker nodes, right? So if we have such an RDD, one way to split the data between these worker nodes is like this, right? So for example, this guy takes care of partition 2 and 5, this one 1 and 3, so on and so forth, right? Simple example, typically we have more machines, we have many more partitions, right? And it may not be as balanced as what I show here. It might be the case that one has only 1 partition, one has like 3 partitions, things like that. That makes sense, and it's fine. So this is the physical view, okay? Is there any question about this? It's very important to understand how an RDD works because it's basically the fundamental component and the building block for all of these programs. Happy? Okay, it's a smaller class, so let me know. If you remember, we mentioned caching last time. We said if we want to reuse an RDD, it's best to cache it, right? Because there's this danger that after the first time we access it, Spark may evict it or remove it from the RAM, and then we have to recalculate it the second time. But if you know that you're going to reuse it, tell the Spark that, hey, I'm going to reuse this, so keep it in memory, cache it, okay? The performance gain depends on how much we cache and how much we can cache, right? Because sometimes in some cases we cannot cache everything because we don't have enough memory. So here's an experiment that shows you how much performance gain we have. So the y-axis is execution time, so lower is better. And then on the x-axis, we show you like if we cache this much, how much performance gain we have. So if we don't have any caching, it takes this particular program or example that I'm showing takes about 70 seconds to run. But if you cache everything, if you do, the running time is reduced to 12 seconds. It's a huge improvement, right? From 70 to 12, that's a huge gain. So as you can see, it has a big impact. So you have to be careful when you program. You want to reuse something, cache it. Very simple, right? You use this particular RDD or variable more than once after this. If yes, use it, use cache. Now, fault tolerance is a very interesting concept, and this is one of the fundamental differences between Spark and Hadoop. In Hadoop, the way we achieve fault tolerance is by replication, right? We keep multiple copies of everything, right? So if one of the machines die, we can use another machine. We have another copy of the data. So the data is actually never lost, right? Because there's a copy. In a Spark, it's very different. It doesn't keep another copy, which means that if one of the machines dies, all of the partitions on that machine are lost. There's no copy of it anywhere. So it is really lost. So, but how can a Spark recover from such a failure? By keeping track of how these RDDs are created, or technically keeping track of lineage information. What does that mean? It means that, again, how do we create these RDDs? Let me show you an example. So we have an RDD here, right? It's coming from this RDD, which is from file, for example. So we read a file, for instance, and then we apply a transformation filter, and then we apply another transformation map. Okay, so Spark tries to remember, okay, how did we create this RDD messages? We created by applying filter, right? First map and then filter, and then that one was coming actually from a file, right? We read the original RDD from file, so it remembers. Now, if one of the machines fail, right? Spark management system will try to find another server that's idle, okay, who can run this. Okay, now you take over. And then how can I recover those lost partitions? Well, we know how we generated them in the first place, so we can regenerate them, right? Now, it is actually pretty smart. It doesn't go to the file immediately to regenerate it. It says, this particular RDD was the result of a map operation on another RDD, right? So let me first check to see if that RDD is available, because if it's available, that's the quickest way to recover, right? So the previous RDD is available, I apply the map again, and I get my data, right? If that RDD is not available, how about the previous one in this chain, right? In the lineage information. In this chain, I go back to the previous RDD. Is that available or not? If that's available, then I apply filter and map, and I recover. The worst case is that none of the intermediate RDDs are available. In that case, in the worst case, we are still fine, right? We go back to the disk, we read the file, right? Or the partitions that we care about. We apply filter and map, and there we go. We regenerate the lost partitions. So it's just a matter of delay or latency, right? If we have some of the intermediate RDDs in memory, is still perfect. We can regenerate. It will be very fast. If that's not the case, it is still fine. We recover from this. Questions? I almost lost my voice because this is the second lecture back to back. I think I won't be able to talk by the end of this lecture. All right. Feel free to ask questions, talk, so that I don't have to talk for a few seconds. So that's the fault recovery or fault tolerance mechanism. As you can see, it's very different from Hadoop. All right. How can we program with RDDs? Before we can program, sorry, the driver code, the driver program is just Python. It's just regular Python on a server, right? So, but how can we actually ask the worker nodes to start doing this Spark stuffs, right? This is the entry point. This is how, and I will show you exactly how. This is the entry point to Spark functionality. So it's a variable called SC that we can, either it's available to us or we can create it, as I will show you. And that will be the entry point. Using that, we will be able to basically tell the worker nodes, hey, do this, right? First things first, how can we build RDDs? How can we create them? A few different ways. The first way to create RDDs is by converting a Python object into an RDD. So you have your Python program, you want to just make, for example, you have a list like this, right? This is Python, right? List 1, 2, 3. You want to make an RDD using that list so that you get an RDD that contains 1, 2, 3 as its values, right? Yes, it's possible. So use that SC variable that I told you, and then there's this useful function called parallelize that takes a host language object, in this case it's a Python object, it's a list, and makes an RDD. For example, if I store this in something like R will be an RDD that contains 1, 2, 3. Makes sense? Where is this guy actually stored? On the worker nodes. Where is this list stored? It is on the driver program because it's just Python, right? Makes sense? So it's basically moving an object from the world of Python to the world of Spark. As you can imagine, we cannot build very big RDDs using this technique, right? Because if this object is already in the memory of my driver program, and if it can handle that, why should I use a Spark, right? And this is basically used for testing our programs, okay? Just for a toy example, or just a small input to test to see if the program is working. Usually, the normal way of creating RDDs is something else. We typically read data from a file, right? We have a data set that we want to process, right? So the data is in a file. Can we read it? Yes. So again, Spark provides different functionalities. So one of them is text file, is specifically designed for reading text files. And I think that's all we use this term, because I think all of our files are text, but there are some other variations as well. So you can just provide the name of the file, right? Or a bunch of files. See, you say read all of the .txt files, right? Or even more interestingly, read it from Hadoop. Or even nicer, read it from Amazon S3. That's interesting. So this is the cloud, right? So if your data is on the cloud, Spark provides a mechanism to connect your data to the cloud without having to download all of your data to your local machine or your cluster and then run it, right? That's very convenient. So, and it has many other connection types as well. So that's nice. So that's typically how we read files. Now that we have created RDDs, how can we do our different operations? Basic transformation. So here's an example. So I again use parallelize to create an RDD. The values will be 1, 2, 3. Now, the first operation that I want to do is a transformation called map. Okay, map takes every element of the RDD and does something with it. Okay, and that something is defined by this lambda function. It says take every element x, right? So you can think of this like a loop, that the first time x will be 1, the second time it will be 2, and last time it will be 3, right? If you have a billion elements in your RDD, same logic, okay? So for every element x, do this. Raise it to the power of 2. So in Python, we can just multiply it by itself, right? Just calculate the square of that value, right? So what happens is that if you apply, so do you agree that this is what I have in my RDD, right? So for every element like 1, it does this, and it creates a new value. So 1 multiplied by 1 is 1, and then 2 multiplied by 2 will be 4, and same. 3 by 3 is 9. So this gives us a new RDD. Remember, we don't modify nums, right? RDDs are read-only. We cannot modify them. If you apply transformation on an RDD, that gives you a new RDD. In this case, the squares. Okay, these are just names that I chose. It can be anything. It's like variable name, right? Squares, and this will be a new RDD that contains 1, 4, and 9. Make sense? Let me know if there's any questions. So we have other transformations such as filter. Okay, filter is very useful because when we read the data set, sometimes 90% of it is garbage. We don't want it. Okay, so filter is your friend. Apply filter on the first RDD and get rid of the data that you don't want. Okay, so it says, okay, for every element, so now I'm applying it on the new RDD squares, right? So I'm working with this thing now. So it says for every element x, so again, think of it like a loop, that the first one, x is 1, then it's 4, and then it's 9, okay? Keep it only if this statement is true. X mod 2 is 0, so the remainder of the division of that number by 2 must be 0, so it's divisible by 2, right? 1 is not, right, because the remainder is 1. 4 is okay, right? The remainder is 0, and 9 is not because the remainder is 1. So the result of this will be a new RDD again. We call it even, right? We want to keep only the even numbers in that RDD, and it will contain only one value, 4, because that was the only one that made this statement true. All right. Again, remember, this is a pretty stupid example. I only have 3 numbers, right? We would not use Spark for something like this, right? Because it is like going grocery shopping using a cargo train, right? We don't do that, right? This is for demonstration purpose only. We typically have a lot of data, right? These RDDs can contain like gigabytes of data, right? That we cannot do on a single machine, or it's very difficult. All right. So last thing I want to show you here is another type of map called flat map. Let's see what it does. All right. Let me go back to map first. Let me ask you a question. So I have this RDD nums, okay? And I apply this map on it. So basically, I calculate the squared value for each element, okay? If I tell you that there is 1,000 elements in nums, how many elements do I have in the resulting RDD? So if the input RDD has 1,000 numbers or 1,000 elements, and if I apply this map operation, how many elements or numbers I will have in my resulting RDD? Same number, correct, right? Because what we do here, for every element, we do something, right? So here for 1, we did something, right? Did this, and then, so another thing. So do you agree that this is like a one-to-one mapping? So we have 1, okay, this is too dirty. So it's a one-to-one mapping, agree? So 1, and then apply something on 2, right? We apply something on 3, agree? So map is a one-to-one mapping, right? So if you have 1,000 elements, you get 1,000 elements. Here we have 3 elements, we ended up with 3 elements, same number, right? Flat map actually doesn't follow this rule, and it can give you a resulting RDD that has a different number of elements in it. How? So for example, here I say for every element x, okay, and it's still I'm using the original nums RDD, okay, so the input RDD has 1, 2, 3. So it says for every element, apply or make every element distinct. Range of x. Range of x is another list actually. That's basically a list of numbers from 0 to x minus 1. So if you give, so basically range 5 is 0, 1, 2, 3, 4. Okay. So now you agree that if I have a number in my original RDD, which is 5, in the resulting RDD, I will have like 5 elements. I had 1 element before, but now I have 5 elements, right? Instead of that 5, I will replace that with 0, 1, 2, 3, and 4. This is not the behavior of map, but flat map allows that. Okay, so we can have basically a 1 to n mapping here. So for every element that I had, it can be mapped to different number of elements. Okay, 0 to infinity. It can't be infinity, but anything basically. So what happens if we apply flat map and this thing in this particular operation on nums? It will be, so 1, range of 1, what is that? From 0 to 1 minus 1, so it's just 0, so 1 becomes 0. And then 2 becomes 0, 1. 3 becomes 0, 1, 2. So you can see that I started from an RDD that contains 3 elements. I ended up with an RDD that contains 6 elements. So it's a 1 to n mapping between the elements, right? So it is technically like when you apply map on something like, and then using something like this, it will give us a list of lists, right? Because every element becomes a list, right? So the result will be list of lists. Flat map actually removes or flattens all the inside lists and give us just one list that contains all of the number, right? I will show you more examples in the demo. Hopefully it becomes completely clear. Right. What I showed you was transformations, right? Transformations take an RDD and they give us another RDD. So we start on a worker node and we end at a worker node, right? So we start and finish on the same node, right? Because we start an RDD, we get another RDD, which is also on a worker node. But actions are different. Actions return data from worker nodes to the driver program. Okay, now, so the overall logic of a Spark program is like this. We start from the driver program. So what you write, the program that you write is your driver code. And then the driver code initiates some Spark operations, right? So for example, read this RDD or create this RDD, apply these transformations. And when you're done, return the results to me. So you start from the driver program, we do a bunch of Spark operations, we go back to the driver program typically, right? And the actions help us to go back to the driver program. And one way to do that is using the collect action. A very dangerous operation. You should not use this in your assignment, and you will lose mark for it if you do. And unless otherwise specified, unless we explicitly say return everything. But it's a very dangerous operation because it returns the content of the RDD back to the driver program. And if your RDD is like 10 gigabytes and you run collect on it, the worker nodes will push that 10 gigabyte of data back to the driver program, and you crash your driver program potentially. Okay, but for small examples like what we have here, it's totally safe to collect nums because it contains 3 integers only. Obviously, it's fine. The safe alternative to collect is take. You may say, hey, but I want to inspect the content of my RDD. I'm programming something and I want to make sure that everything is okay up to, until now before I move on to the rest of the assignment, right? I want to make sure everything is fine. So sure, you can inspect content of the RDD by using take instead. Take returns a subset of the elements in an RDD. Okay, and this number, it tells you how many. So if you do take 2, On nums, it returns only the first two elements, which are 1 and 2. It's safe. Now, independent of how big nums RDD is, you can do take 2 because it always returns 2. Now, if it has 5 elements, returns 2. If it has 2 billion elements, returns 2, right? So the amount of data that you send back to the driver program is the same, and it's totally safe. Other very useful action is count. Sometimes you don't care about the content of the RDD, but rather you want to see how many elements you have in your RDD, either for debugging purposes, or that can be the result. That's like all you care about is like how many elements I have in the RDD. Then do not use collect or take. Instead, use count. Okay, count will just return a number to the driver program, which is like how many elements do we have. For example, if we run count on nums, it returns 3 because we have 3 elements. If it has 2 billion, it returns 2 billion. It's still a single number, right? So safe and fast operation if you want to know how many elements. The last action I want you to know is called reduce. Please don't confuse this with something else that I will talk about soon, and that's reduce by key. That is a transformation, not an action. This is reduce, and it's an action. How does it work? It basically collapses and aggregates the contents of an RDD and then returns the merged or aggregated value, not all of the values. What do you mean? For example, suppose that I have a bunch of numbers in the RDD, okay? I don't care about those numbers. What I care is the sum of those numbers, right? For example. So one way to do this is to collect all of those numbers and add them up myself, right? Very bad. You should not do that in your assignments. That's a very bad approach because you should do all of the calculations on the worker nodes as much as possible. You should not just download everything and then you add them up yourself. You should ask them to add them up and send you the results. So how can we do that? Reduce. Reduce says, hey, collapse all of these numbers into a single number. And the way you should aggregate is by this definition that I give you here. So you take two elements like x and y, and you collapse them into a single number by this operation. So take 1 and 2, apply that operation, that will be 3. Then take that element and apply that operation again with the next one, that gives me 6. So you continue doing this, right, for all of the elements, right? And you reduce all of those values to a single number. And then that final number is returned to the driver program, not the numbers themselves. Okay? That's why it's an action, right? Because it returns the result to the driver program. As you will see, the similar operation called reduce by key is a transformation that takes an RDD, it creates a new RDD. It doesn't return anything to the driver program, it creates a new RDD. It's a transformation. But this guy, reduce, is an action. Questions, please. Albert, go ahead.
I just wanted to ask about like the syntax or form of this. Is it bad form to combine transformations and actions? So like we did the num.map and then we squared it. Then what if we do .reduce in one line? Is that bad or is that fine?
No, that's okay. For the sake of readability, it's fine. And if the line is too long, you can break it. It's fine, right? So you can hit enter and write the rest of it on the second line for the sake of readability. So if you don't need any of the intermediate RDDs in the chain of operations, totally fine to chain all of them together.
Cool. Thanks.
No problem. Other questions?
I have a question. So
Yep.
the reduce, I guess, sort of function, is it more of a n-to-1 mapping then? So sort of like the opposite of the reduce map, or sorry, the other function that was 1 to n.
Are you referring to Hadoop reduce or?
No, just like this last reduce you have here with like merging elements
Right.
on the slide. So yeah, I'm just wondering, like, so will this always output like one value, this reduce function?
Yes. Yes. So it basically reduces everything to one element, okay? And then in this case, every element is a number, right? So when you reduce at the end, you get one number. If each element I have here is, for example, a key value pair, for instance, right? So instead of 1, we have Waterloo 1, right? A pair as each element. And then I have other key value pairs. If I apply reduce, I ended up with one key value pair. So whatever your element is, right, you end up with one of them at the end.
Okay. So you're just so like in your example there with like the arrows and how you're sort of like branching off, you're just sort of calling it more than once then, right? Like the
Yeah, so Spark goes ahead and basically start adding up all of them, adding up because that's what I asked it to do, right? I could ask it to multiply the values, right, or do something else, right? Doesn't matter. So here we said let's add them up. So that's what the Spark did, and we had numbers. So when we apply that operation on the numbers, we end up with a single number at the end.
Okay. All right. Thank you.
Yeah, no problem. Does the reduce function work sequentially or in random order? I believe what happens is that, remember that the data lives on multiple machines, right? So imagine that this list is long, like it has like 2 billion numbers in it. So it's on different machines. So I believe what happens is each machine will add up its own numbers, right? So this guy has like 1 billion and the other one has 1 billion, right? And then they add up their own numbers and then they add up the results and they send it back to the driver program. That's how it works. Good questions. All right, other questions? And the final, let me know if there's any other question. The final action is saving the file. Sometimes we don't want to return anything to the driver program, but rather we want to save the results, right? Back to disk on the worker nodes. And we have a very useful action called save as text file. So it says whatever my RDD is, store it to disk, and you provide a file name and it stores it to disk. It can be local or HDFS, depending on what file system you have. It just stores it for you. That can be also useful sometimes. It is very common to work with key value pairs, right? You probably got an idea already that key value pairs are very useful for what we do typically. And for you guys, you should focus on this syntax. So you can create a key value pairs in Python very easily using parentheses, key, and then the value. If you want to get access to key or value, it will be square brackets and then an index, index 0. It's like a list, right? Index 0 is the first element, which is the key, and 1 will be the second element, which is the value, right? So that's how we work with key value pairs. So it will be a very useful syntax for us. We got another question. Is there any Lambda functions that wouldn't make sense with reduce? For example, here you are adding the terms, so it makes sense that you will reduce to a sum, but what if I call reduce with a Lambda function that does nothing. Yes, you will get a syntax error. So so it should be a function that takes two elements, okay, and produce a single element. So that's the requirement. So that Spark can keep doing this and apply that on to all of the elements of the RDD. It must be something like that. I think otherwise it gives you an error. We can try this today if you have time. Remind me later. I don't think it works. All right. So key value pairs, how to define, how to access key and value. And we obviously have some operations on key value pairs. So to show you the example, let's create a new RDD called pets. And each element is a key value pair. Okay, the key is either cat or dog, and the value is a number. Okay, that's my RDD. Now, there is a very useful operation. This is the one that I told you not to confuse with reduce action. This is reduce by key. It takes an RDD and produce a new RDD. What it does is exactly like the reduce operation of Hadoop. Okay, so reduce by key, what does it do? Well, we have to define this in this lambda function, right? It says for two values like x and y, because in reduce by key, you do something when the keys are identical, right? For example, here, cat, cat. I have two keys that are identical. So now the question is, how can I aggregate their values? And this is what this function is saying. It's saying for two values like x and y, in this case 1 and 2, right? Two values, add them up. What happens is that the resulting RDD will have a key value pair with key cat and value 3. And obviously, if there are more cats, we add them up as well, right? We add up all of them. And then in this example, there is no other key dog, like dog, so it's the same one, so it's 1. So as you can see, we started from an RDD, we end up with an RDD. Nothing is returned to the driver program yet, right? So it's a transformation, not an action. We have another question. Why did it assume that the key is the first element? Well, this is the assumption, basically. So this is typically how it's defined, right? We consider the first element to be the key. Just an assumption. Okay, let me clean this up. Oh, no. We have other operations on key value pairs. A group by key. It's exactly like reduce by key, except that you just create a list of all of the values that share the same key, right? You don't reduce them. You don't apply any mathematical operation on the values. You just group them, right? Say cat 1, 2, right? And then we have sort by key. That's useful sometimes. So in this case, we want to sort these elements based on their keys, right? And in this case, keys are a string, so we sort alphabetically. So cat is smaller than dog, right? Because C appears before D, right? So these two, cat, and then dog. In this case, it happened to be the values are sorted as well, but there's no guarantee on the values. We do not sort the values. We just sort the keys, okay? This is just coincidence. It could be cat 2, cat 1. So sorting the keys. All right, now let's write some programs, all right? We don't need the slides anymore. Can you see my screen here? This is Colab. All right. Is the font size okay? Let me know, guys, in the chat if the font size is too small. So we want to write a program, okay? So the difference here now compared to assignment 0 and assignment 1 is that we want to do actually do something in a Spark, right? Those assignments were Python only. Now we have to have Spark. So Colab doesn't have a Spark by default, so we have to install it, okay? So this block of code actually downloads and installs the Spark for us, okay? And you can do this on any server. It's a convenient block of code. And we will provide this in assignment 2, okay? In assignment 2, you start using a Spark. So sure, zoom a little bit, see if this is better. So this is just downloading and installing Spark, all right? So don't need to worry. This tiny marker here, the green marker, shows which line it's executing. So this will take some time, 30 seconds or so. But that's the first time we want to open the notebook. After that, it works. If you close the notebook and open it again after a while, I think you should do it again. So don't worry about this block. We will provide it for A2. All it does, it installs a Spark. Okay, it's done. Now, the second block, again, we provided to you, is we create that SC or Spark context, right? This is our pointer or a reference to do something in a Spark, right? Again, this block is provided to you. So all it does, it initializes your Spark context so that you are ready to code in a Spark. And this line is just, I'm downloading a data set and nothing is special about this. All right, let me add a new block of code. And now we can basically test a few things. All right, so let me give you a basic example to make the point about where the data lives, right? Because that might be something a little bit confusing for you guys. This is an array, agreed? A list, sorry, in a Spark. In Python. And by the way, today I had 2 lectures. In one lecture, I use a Scala and the other one Python. So I will make mistakes and you can make fun of me. So this is Python. This has nothing to do with the Spark, right? So if I print this, what is it? It's just a list, right? Now, what I do, I use that parallelized operation. If you remember, it takes a Python object and it gives me an RDD with the same content, right? So in this case, I can either do like 1, 2, 3 here, right? Like that, or just give it test, right? So I say, hey, give me an RDD with this content, right? Now let's print my RDD. Okay, the first one is for test, right? And the second one, what the hell is this? What happened to the values? So it says this, what I'm printing here for you, this is a parallel collection RDD. So it means it's an RDD, okay? So it says, hey, I am the driver program. I don't know the content of this RDD. All I know is that this is an RDD. This is like a reference, right? Where is the data? The data is on worker nodes, right? So it's not here, and we should not expect it to print 1, 2, 3, 4, 5. Makes sense? In order to get access to the content, you can use one of those actions that we just talked about. So on my RDD, you can run collect. Again, dangerous, but safe here because we only have like a few numbers, right? So we say, hey, collect it. This is telling the worker nodes, hey, I need my RDD data. Give it to me, okay? So I run it again. Bingo. It's the same data, right? Because now we get the data, we print it, everything's fine. So we got a question. Where are the worker nodes? On a real cluster, right, where we have multiple machines, the worker nodes are different servers, different from us. So I'm one of the servers, and there are other servers, physical machines, different physical machines. So they are, it's like physically a different machine. That's a good question, right? So that's where the data is. The data is on other servers. So when I run collect, we use the computer network between these machines to move the data to my server, and then I can show that data.
Yeah, sorry. So like when we actually create an RD in Colab, where's like the actual data is stored? Like how is this free? Like this is what I'm thinking of. How is Spark
Okay, makes
is allowing
sense.
to do that for free?
Good question. Okay, so when we, how about here, explicitly here, what's happening here? So here, this is a standalone installation, right, that we did on this machine. This is a single machine. I installed Spark on this single machine, right? Your point is there's no cluster here, right? So when we have something like this, when you run Spark on your laptop or on a single machine, it simulates it for you. Okay, so basically it simulates different machines by different threads. Are you familiar with the threads in programs? Like sub processes, like it's like sub processes. So this program is like creates like copies of itself, for example, right? And then each copy acts like a worker node, right? Although it's running on the same physical machine, but we are basically mimicking that behavior by having like separate processes. You can think of this as each worker node is a different program running on the same machine, for example. But still, the driver program doesn't have that data, right? It's somewhere else. Although it's physically on the same machine, but that particular process does not have the data. Make sense? So this
Yep.
behavior is exactly the same if you run it on a single machine or an actual cluster of it that has like 1,000 worker nodes. Exact behavior. So we got a question, is it process level or thread level? I believe it's a thread level on a single machine. So each worker node is like a different thread. So so that's what we have. Okay. Test, let's review this. It's very important, basic but very important. Test is a variable on the driver program. So it's in the RAM of this machine, of this process. Okay, think of it as a cluster. So the driver program is one machine and worker nodes are separate machines. Okay, this is easier to understand. So this is on the main memory of my computer, right? And I test it and you get the values. You create an RDD using it, and that returns a reference to you, right? That you can provide to Spark to say, hey, I mean this RDD, right? It's just a name or a reference to RDD. The content is not here because that's the whole purpose, because this idea behind RDD is that the data is too much that I cannot keep in the memory of a single machine, right? So we just have a reference to it. The actual data is distributed over hundreds or thousands of machines in reality. In order to get access to it, you have to run collect so that we bring the data into the driver program, and that's why it's a very dangerous operation. In my stupid example of only 5 integers, is totally safe. So that's about that. Understanding where the data is, right? Important, very basic. Now let's move on. Let's do. So let me go back to my notes to make sure that I'm not missing anything. All right, so let's do some basic operations here. I can just keep adding stuffs here. So I have my RDD, right? Dot I can, for example, filter. I want to keep only even numbers, right? So here the lambda function should say I only want even numbers. So 1, 2, 3, 4, 5, I only want to keep 2 and 4 because those are the even numbers only. So it will be lambda x for every element, right? For every element, I only want to keep it if this statement is true, okay? I can store this in a new RDD called even, right? And then I can just do even dot collect. In a Colab, you don't actually have to use print. So when you do something like this, it prints it for you. So let's see what happens. There you go, right? So even is the subset of the original RDD that only contains the even numbers. Now, for the sake of time, let me copy stuff from my note. So that was one way of doing it, right? And let me just add the stuffs here. Here's a function definition called is even, right? This is a function. This is a Python function. It has nothing to do with the Spark. It takes an element, a number, and it returns true if it's even, and it returns false otherwise. Makes sense? Simple Python function. The reason I defined it is this. I want to show you that. Let's call this even 2. On my RDD, instead of inline definition here, instead of lambda function, I can use an already defined function. And the assumption is that that function takes an element and outputs true or false. If that function has this properties, you can use it. So it's exactly like this. Here it has inline definition. So here you define what you want. But you can also refer Spark to a defined function. Why should we do that? Because it looks like it's just more work. It's cleaner here. Because if this operation is more complex, writing it inline will be messy. If you need to do a lot of calculations, then it's best to define a function separately. It just cleans up your code and makes it much easier to understand, right? Because I know that this is what this function does. I don't know how it does it, right? All I know is that this function returns true when it's even and false when it's not even. So I can say my RDD.filter is even, right? Easier to understand, right? Especially if it's a big program. So this should be the same. So if I do even 2 dot collect, give me the same thing. What happened? There should be another line here. What? For some reason, it was not collecting one of them, I think, because now that I've commented this out. All right, thanks for reminding me. It's because I think it only works if it's the last line. Thanks. That's why. So if I put it in print, it should print both of them. One doesn't need to be inside print, but there we go. Thank you. So the issue was that without the print, it only prints if it's the last line. That's why I had one here and one here, and only the last one was printing. That's why. But if you put it inside print, it prints all of them. Okay, so now both of them print the same. So same logic, different ways. Inline definition, dedicated function implementation. Makes sense? Now, let me know if you have any questions. Moving on. Let's see a real example here. All right. Let me define a new RDD. And I use text file this time. Instead of the dummy example, I want to read a real file. And you're familiar with this file already, right? This is the Shakespeare file, right? let me actually show you something interesting. Let's make the file name wrong. Let's run it. Yeah, it said, I have created an RDD for you from this file, right? It's an RDD, everything's fine. It's lying, right? Because of lazy evaluation, because we don't have any action. Now let's, if I change that, add an action here. Really, you create an RDD, give me the first line now. Said, oops, there's a problem that I cannot, input path does not exist. Okay. So, but if I give it the correct file name, this should give me the first line. Okay, give me the first 10 lines. Give me the first 20 lines. The first lines are mostly empty. You don't see much. So, okay, cool. We could load the file, right? That's interesting. Now, I want to implement word count quickly here. All right, so let's see if we can do that. Cool. So we have the lines. Now, what we want for word count is first we have to tokenize, right? So we get like an array of all of these words, right? Before we can start. In your assignment 1, you use a tokenizer, right? I can do that, but I'm lazy. I implement my own tokenizer, which is not as good. So I can do map, and then I say lambda. So for every x, for every line, x here is a line, right? For every line, do this. X dot split is a Python function. So split that line. For example, take this line and then split it by space. Not the best tokenizer, because I should use other stuffs as well. But like for now, for the sake of this example, I just do that. Okay. Let's see what happens. Take 20, let's say. All right, so if we ignore the first lines that are mostly empty, then okay, like for a line that we had before, now it's tokenizing it, right? 2 words. I'm extracting the words out of it. Okay, so that's good. Now, there's an issue. The issue is I don't have one array. I have a 2-dimensional array. See, this is the main array, right? And then for every line, I have another list. Sorry, I keep saying array. I mean list. Like this is list of lists. Basically, it's map. If you remember, map is a one-to-one mapping. So it takes an element, which is a line when we work with text, right? It takes a line and it gives us one object because it's one-to-one mapping, right? So that object is the list of words that we have in that line. Make sense? So this is not good for a word count. We really want one list. We don't want 2-dimensional lists, right? So we want one list with all of the words in it so that we can start processing it, right? So the issue here is that list of lists, right? I want to get rid of these inner lists. So flat map is our friend in this case. If I change map to flat map, if you remember, we said it does the exact same thing, right? It calculates this thing that we have right now, but it flattens the results. So it removes that second dimension, right? It makes it a 1-dimensional list. Run it again. There we go. See, there's no other lists, right? It doesn't print it nicely if you really want, I think. If you print, no, I cannot do that. But I can just put the whole thing in print. It's nicer. It's same data, right? It's just nicer in one line, right? So these are the words that we moved. Previously, when I took 20, it was returning 20 lines. That was the object. But now each object is a word, so 20 lines will return less data. So if we need to see all of those other words, we need to take more. These are the words when they start, right? Makes sense? So this is ready now. So we have like an array that contains all of the words. We are good to go now. Let me remove this print. All right. Any questions about this? So basically flat map is like map, except that it removes those inside lists, right? Flattens everything for us. Cool. Now that we have this, we can use word count, and we can use the same logic that we learned for Hadoop, right? So we can have a map that for every word that we process, we emit a key value pair. The key is that word, and the value is 1. And later on, we can do reduce by key, and we add up those ones to figure out how many times each word appears in this text. Makes sense? So on this, I apply a map. And remember, it's like a for loop that this thing is called for every word that we have in my RDD, right? Simple. Don't worry about that. This can be a gigabyte of data. Doesn't matter, right? But this is hidden from us. This is the beauty of this abstraction. We don't care, right? We just tell you what to do to every word or every element that you have. I'm telling you that for every element, which is a word in this case, convert that to a key value pair where the key is that word and the value is 1. So the result of this will be exactly the same, except that every word will become a key value pair and with the value of 1. If I do take 10, you'll see, or 20 maybe. See, every word is now a key value pair, right? Cool. The last step would be to reduce by key. Now, okay, take and for example, see how many Shakespeare we have, right? So all we want here word count. So I want to add up all of the ones. So for every 2 values like, sorry, lambda, x and y, let me cheat quickly. I'm confused between Python and Scala. Yeah, okay, that was correct. For 2 values, x and y, in this case, it will be 2 ones, right? What you need to do is x plus y. Add them up, right? And let's store this into results that RDD. It immediately returns and says I've done it, but it's lying, right? Because we don't have any action. In another block, I can do, let's say, result.take 20. Show me the first 20 results. Now you can see that it starts thinking for a few seconds. And now it returns that it says, oh, empty space is these many times. The reason this is returned is that my tokenizer is stupid. The one that you work with doesn't have this issue. It says Shakespeare is appears 38 times, fairness 38 times. Okay, cool. So we have done word count. Now this guy, results RDD, contains word count. Cool. Let's add one more step to this, okay, and then we finish. So let me actually cache it. But the next step I want to do is I want to return the top most frequently used in this text. Okay, right now there's no ordering, right? I don't know which word is used more frequently. So what I want to do, I want to basically sort everything by value, right? So that I see, okay, this, and I expect something like the to appear most frequently, right? Something like I, in, things like that, these are most frequently words. So basically I want to sort based on the values here. But the issue is that, let's assume that we only have sort by key. If we only have sort by key, how can we do this? Because if I perform sort by key, it's not useful, right? If I do sort by key, it returns something like this, right? It sorts them alphabetically. I wanted to sort based on the value. This is not good. Can I use this, but with a trick? Yes. What I want to do is that I have these key value pairs, and I have a mechanism to sort based on the keys, but I want to sort based on the values. So what I want to do is that I want to swap the location of keys and values, and I want to make the value the key. Then I want to sort it, and then I will revert it back to the correct location. So that's the high level idea. Yes, Albert mentioned that. Flip them, exactly. So we want to flip, sort, flip back. Let's implement this quickly. So before I can use sort by key, let's forget about this guy for now. So we want a map. How can we flip? Very easy, very easy. For every element, right? X, oh sorry, confused with the Scala. For every element X, and what is X? Remember, we always say lambda X, but X depends on really what you have in that RDD. In this case, every element is a key value pair, right? So I want to create a new key value pair, but I want to flip the location of key and value. How? Easy. Something like this. I want a new key value pair where the key is the second element and the value is the first element, right? This will basically switches the location of key and value. If I just forget about this, and if I do like take 20 on this, you'll see what happens. See, same data, key values flipped. Okay, now that it's flipped, now we can sort by key, right? Interesting trick. Take 20, see what happens. Cool. The only issue is that I wanted the top most frequently used, but sort is sorting increasingly. We want descending order, okay? And you can just, I think, provide false here. False in Python is like this. This will revert it or reverses the order of sorting. Let's run it again. There we go. Now we have the larger numbers first. This way I can just take 20 and these will be the top 20 words. We got the data, the format is wrong, right? We got a question, will this not give us duplicate keys? It's okay. Duplicate keys is not causing any issue in this particular case, right? We just want to sort and it's fine. You think about the dictionary where we cannot have duplicate keys, right? These are just a bunch of key value pairs. I can have repetitive keys. It's okay, right? Previously, we had repetitive keys. That's how I appears like 19,000 times. It means that previously we had like 19,000 key value pairs where the key was I, right? It's okay. And now the data is fine. Let's just make it the correct order. Basically apply that map again, right? It flips it again and it will be correct. So basically for every element, right? Here, should I say x01 or x10? Help me here. Let's say 0, 1 or 10.
10.
10, same thing, right? This is applied on the resulting RDD, right? So again, on this thing that we printed, and it's nice to print everything, right? Because it's in front of our eyes and we don't make mistakes. So you say, hey, I want something where this thing, which is x1, moves to the first location, right? So we do that. Then take 20 again. Hopefully this is what we want. Bingo. So again, I apologize for not using proper tokenizer, but the rest of them make sense. The I and 2 of A, right? These are what we expected. These are the most common words in English. There we go. Now, you will kill me if I tell you that there was a function for sorting by value. I just did this to show how you can play with key values because it will be helpful in your assignment, because sometimes we want to, because in the assignment, sometimes we ask you to provide or output results in a particular format. And these kind of tricks will help you to print like the first column this, the second column is that, third column is that. So you can use tricks like this. And there's a lesson in this. The lesson is, unlike Hadoop, where we only had 4 functions: map, reduce, partition, and combine. Spark has a very, very rich API. It has many operations, okay? Whenever you want to do something, search for it, okay? Either API or Stack Overflow, doesn't matter. See if what you want to do already has an operation. If it has, just use it. And for example, for this case, there's an operation. I let you look into this, but instead of all of what we did, because we could just do something like res.sort by, I believe, and then you have to specify here which column or which index you want to perform the sort based on, right? So this one, or whenever in the assignment, give you a hint. I think in assignment 2, the next one, somewhere we ask you to return distinct elements, right? So one way to do this is to calculate distinct yourself, which is bad. And typically students pull stuff to the driver program and do that, which is really bad. You'll lose points. Actually, Spark has a distinct operation. So you can apply distinct, for example, on an RDD, and it gives you distinct elements, right? You will use this for the next assignment. So my point is, search to see if those operations exist, okay? And you don't have to reinvent the wheel again. All right. Any final questions? I stop here and we continue this demo next time, same time on Thursday, and then we go back to the normal lecture time next week. We will talk about more complex things in Spark in the next lecture. If you find operations should be a source where we found it, no, we don't have to, because the source is the API basically at the end of the day, right? It's the API. But if you do something that's specific, for example, in a function that has like 5 lines of code, right? If you do some operations in a specific order that you have seen somewhere, that should be cited in your code, okay? But you are free to use any operation here. There's no restriction, so you can use anything that you want. But remember, if you use something from Stack Overflow, part of it is okay, right? That's how I program, and that's totally fine. But looking at other assignments is not okay. And as I mentioned previously, we will run a program that finds similarity between assignments, even if you use different variables, if you add comments or try to move or change it, it still finds it because it works based on the logic of the program and not your code. So it finds, and it will be bad consequences. So thanks for reminding me to talk about this a little bit. I'll stop recording here. I will be around for a few more minutes. If